Okay, so we'll start with a simple experiment, and then for chemistry major, I mean this book did a really good job on describing various natural and industrial chemical processes. A lot of stuff like I don't know about these processes, but it's something that's good to know. So if you're interested, I would suggest you guys to look into it, but it's not mandatory, but it's more of common sense for chemistry. All right, so we have this solid, which I'll describe the chemistry that happens later on. Okay, so a white solid, and I also weigh out some white solid in here. And then I'm gonna mix these things together, and be very careful. I'm gonna pass this bottle around, and just feel it with your hand, okay? So I put two solid together, and I shake it for a little bit. And you can see it getting moist, right? It looks like there's water forming in this bottle, okay? So I'm gonna shake it up a little bit, and then this reaction is self-accelerated, and I'll explain the chemistry in a little bit. Okay, now it becomes a slur. You can feel it with your hand. Be careful, do not drop it, okay? It's not gonna smell very good. Just feel the bottom of the flask and the top of the flask, and just pass it around carefully. So from a chemical reaction, we know the delta G has to be 0 for a reaction to happen spontaneously. And from this bottle actually gets cold, so that means it's removing heat from your system, right? That means it's endothermic. So this sign is positive. And since this reaction was simply triggered by shaking the flask, and that is just to encourage the mixing between these two powders, it happened instantaneously, so we know that delta G is 0. And the term delta T is in Kelvin, right? So the lowest possible number is 0 Kelvin. This is a positive number. So in order to keep the delta G negative, keep this reaction spontaneous, what's the sign of your delta S must be? Plus, right? And it has to be much larger than delta H, okay? And we know the unit for delta H is in kilojoule, and delta S, the entropy term, is usually in joule. So this delta S has to be very big for this reaction to happen. So this reaction that you saw was mixing barium hydroxide with ammonium chloride. And remember from the acid-base chemistry, how do we get this? It's mixing ammonia with HCl, right? This is weakly acidic. It can easily give off a hydrogen to a strong base, forming water. So I'm too lazy to balance the equation. But basically, once it mixes, you're generating water, right? And water dissolves your starting material. That's why you end up as a slurry. And that's what I mean by self-accelerating. Your product is actually encouraging or accelerating your reaction because you're dissolving the salt, creating more interactions, because we know as a liquid state or aqueous solution, the movement is much faster than its solid, right, form, right? If you're looking at this reaction, we're gaining a lot of entropy. And the ammonia, even though it's formed as a gas initially, it likes water, right? So it will immediately deprotonate water to generate ammonium hydroxide. So this is an example of an endothermic reaction that can occur. So when we think about dissolution of salt, it could be exothermic and it could be endothermic. It's really depending on the type of salt that you're dealing with, and has to do with the solvation energy. For this reaction, if you use the heat of formation and the standard delta entropy, you can calculate for this reaction at room temperature, its delta G is negative 46.1 kilojoule per mole of these reagent. I know the idea of kilojoule is very vague, but we know Gibbs free energy has to do with work, right? So if you think of it in the physics term, this is about lifting up 100 kilogram of object from the floor to about a meter high. This is how much energy in 1 kilojoule. So for our daily consumption of energy, we usually use calorie, right? So you can convert this value to calories, so that gives you a sense of how much energy that is, okay? So chemicals has energy. So a lot of processes, we use chemical energy and then convert it into something else. A great example is burning fossil fuels. I think now we'll move on to our electrochemistry, and this will be the last lecture on electrochemistry. So remember, delta G has to be negative to be spontaneous. And previously we learned that if this is your standard potential relative hydrogen is larger than 0 for your photovoltaic cell, if it's larger than 0, then it's a spontaneous process, right? So how will we connect these two terms together? So I would like you guys to think about potential as a difference in energy. And in a redox process, when you balance the equation, electrons term goes away, right? But during the steps that you do to balance the chemical redox reaction, you will count the electron and they have to balance. So the electrons are the ones that are actually doing work in these processes. So while we can describe an electrochemical reaction using delta G and consider the enthalpic and the entropic contribution to this final energy, there's a simpler way to do so. Faraday, there's a thing called a Faraday constant. So he is actually the founding father for this field, electrochemistry, as well as electromagnetic system. Okay, so we consider the work done by a battery is related to its potential difference times charge. Okay, so electron has charge. It has the unit of coulombs. And then so usually it's because this is the battery doing work on its surrounding, we have a negative sign in front of it. And then the charge, it really has to do with the number of electrons involving in this process that is transferring between your cathode and your anode. And then by convention, we said for the voltaic cell, your electron goes from anode to cathode. Okay, so always remember anode to cathode. I already taught you guys multiple times to remember where the reaction happens, okay, where the redox happens is you remember anode, A is before cathode, because we did a simple alphabetic order. And we say oxidation and reduction, 氧化还原. So your anode is where oxidation happens. Okay, but when you're charging a battery, you're reversing the direction of electron. Where anode become cathode, cathode become anode. But still, the oxidation and reduction still happen at the same places. Okay, and we'll have more example in the later section. Okay, so if we balance these two equations together, we can relate it to the free energy of our voltaic cell based on this equation. This is the number of electrons involved in the redox process, and Faraday constant, that is just a physical constant that was measured. Okay, so that is about 96485 coulombs per mole of electron. So in chemistry, we deal with mole. So you can see the charge will be this term, okay? And then remember, by recalling that, we can also get equilibrium constant from delta G, right? The equilibrium constant will look like something like this. And then this is, in thermodynamics, this can be the number of microstates, right? So each of redox reaction that you're doing, it represents how many total microstates that you could have. And when you're looking at the value, it represents one state, okay? So by rearranging this equation, we can get this equation, right? This has to do with the nature of your electrochemical reaction that you're dealing with. But this term is all constant, right? So that's why in electrochemistry, you will see a simple calculation or another constant that will simply give you the conversion between the standard potential and the equilibrium constant. Okay, so for typical battery, these numbers are very big. And then remember, we can look at how far away we're from equilibrium by looking at the delta G with the circle, which refers to the standard state. Okay. If you remember this equation from previously, then we can substituting in the electrochemistry term, this number of electron times Faraday constant times standard potential, substitute this into this equation. Then we can think about a zinc-copper redox process. We can look at the concentration of each ion, because remember when we're writing Q or K, we don't care about liquid and solid. We only deal with the thing in the solution, looking at the ion that actually matters. So we can using a similar equation to calculate how far away you're from the end of electrochemical reaction. And this is also called the Nernst equation. Okay, so if we go back to this, okay, so remember we said the standard potential, so this refers to standard state. Standard potential has to be larger than 0, and physically this, if this is larger than 0, this is a constant, this is always larger than 0, that indicates a spontaneous process. Okay, so then we can do a thought experiment in terms of what's happening. If the Q is less than 1, so that means you have your more reactant than your product. So that means the reaction will go forward. The reactant will want to go to the product side. And then if they're equal, basically this cell is dead. You don't have any more potential to drive the electron. Remember, the reason why electron flows and why it wants to reduce or why it gets oxidized, it has to do with the standard potential. When there's no potential, the battery is dead. It's possible that you get a negative term, okay? That means you are just over the equilibrium. And if you recall the Challier principle, we can apply that. It's gonna go backward. But if you detach the wire, it basically you just stop the system, but it's out of equilibrium. So as soon as you connect the wire, if you make connections, this redox process will occur. Oh, sorry, messed up. Okay, so there shouldn't be a negative sign here. Basically, from this equation, based on the Q, we can figure out how far away we're from the equilibrium. But this is very simple thought experiment that you can do. So if you look at your book, there is a figure called the 21.10. It's on page 960. So you can see a triangle that related the standard cell potential to the equilibrium constant and delta G. And there's a table that summarizes different scenarios and how this is related to the reaction, the certain state that you just observed, and how is that related to its equilibrium position. And based on this equation, now we will talk about concentration cell, okay? Because the redox process is happening, your ion concentration change over time, your E cell is constantly changing, right? But how about we have a system where your ion concentration is different, okay? So for example, here is 0.1 molar copper 2, and here is 1 molar of copper 2. So by applying this equation, there is still a very small net potential to drive the reaction. Okay, so this is the concentration cell. So you can use this for refining copper and other metals. So in reality, this is because there's a concentration difference, we call there's a chemical energy gradient. there are going to be some spontaneous reaction that could happen between these two states. So in order to dilute this, okay, then the copper 2 will deposit onto the electrode, become copper 0, where this side, more of a copper will be oxidized and released into the solution, so to reduce that difference in the ion concentration. And this concept, so before we talk about pH probes, you can use a special probe that you buy to measure the pH. It is exactly the same idea of applying this equation. Okay, so this is a specially made, if you look at your figure 21.13, it's a specially made cell. Okay, so generally it's over 3,000–4,000 Taiwan dollar for each of these probes because they're calibrated, and based on the difference in the proton concentration, right, you can calculate. If you look at on page 966, relative to the standard hydrogen potential, okay, you can figure out the concentration of proton, which is related to your pH. So this is one application of electrochemistry and the concentration cell. Okay, so I think that's all. And then we will talk about electrolytic system. Previously, we talked about voltaic cell, right? And then on the exam, some people also ask me what is galvanic cell. They're basically the same thing. The galvanic, this name is in honor of one scientist that was studying battery, okay? Okay, so we previously studied battery, and we know the standard potential is larger than 0. Your delta G is less than 0 to be spontaneous. So it's releasing energy. It's doing work. The chemical redox process is doing work and provide energy. So the movement of electron can drive other things that you desire to do, such as lighting up a light bulb. For the electrolytic cell, you're doing exactly reverse. The best example is electrolysis of water, right? So you can put 2 electrodes in, and if your voltage is high enough, you will be generating hydrogen and oxygen at the respective electrodes. So basically, you need to attach to another big battery or a reservoir, okay? So that means when you're connected, you're putting energy into a system to drive the otherwise non-spontaneous process. So why reaction happens? If you go back to this equation, think about it. So recall the experiment that we did previously. Now discuss with your partner what's the origin of a spontaneous reaction. Why the chemical energy are willing to be utilized to drive chemical reaction forward. So it's quite simple, right? The law of thermodynamics suggests entropy prefer to increase, right? If you think about enthalpy, if you think about why the melting process involves absorbing heat, right? So you're gaining that enthalpic energy and convert it into entropy. The chemical energy are willing to be utilized. It's because we're increasing the entropy of our system. So for example, if you look at your page 975, generally for a tin copper system, you have a voltage of 0.48 volts. So if you put an external source that is greater than 0.48 volt, if you recall this equation, you're out of equilibrium, right? So what will happen when you're out of equilibrium? Your system will want to restore its own equilibrium state. And this is why this electrolytic system will work. And of course, there's what's so-called overpotential or overvoltage. And that concept, it has to do with you're converting something that was originally dissolved, right, and into a gas. So that transition really also require energy. Okay, so that's why there's such thing called overpotential or overvoltage. It's required for gases to be produced. So that is what accounts for this delta S term. So of course, we can explain why the electrolyte that dissolve in water does not usually produce the corresponding electrolyte product. That's because water is easy to be oxidized and reduced, which forms oxygen and hydrogen. So for a lot of chemical processes, electrochemical processes, sometimes water is your worst enemy because it's easily to be break down before your chemical of interest breakdown. Okay, so for the concept in this, if you go back to the page 975, lead acid battery that is used in your car, we can look at the charging process. The green part is the discharging. That means you're using the electricity generated by the battery. Okay, so you have these redox reaction happening, right? And then for the charging cycle where you put a higher voltage, okay, so then the energy will flow from the higher voltage and higher potential to lower potential, right, to drive the chemical reaction. And as you can see, what the original product become the reactant, right? So you're driving that chemical process. Okay, so why does the battery only have certain cycling lifetime? I would like you to discuss with your group mate. Why does battery has certain lifetime? And why does the battery lifetime decay over time? You should be thinking about this equation. Okay, so theoretically, in your recharging process, okay, you're putting external power supply, you're putting external energy back into your battery. You really hope you can push the equilibrium back to what the fully charged battery was. But however, that process never happened. It's really difficult to go back to the original state completely. There can be many reasons. So the amount of reagent you can work with decrease over time. That's why the lifetime decay. And then so for normal use, we will like our battery can be charged up to 1,000 times or even 2,000 times, right? Because think about your phone, you will charge it maybe once or twice a day. You would not want a new phone in a year. So the consumer's demand will dictate where the battery technology will go. And then there are a lot of chemistry and a lot of physics and material science as well as electrical engineering in designing a circuit that can manage your battery lifetime. We want to be able to use the energy when we need it. Again, going back to this equation, some of that energy is lost as form of heat, right? So if we think about charging battery, normally you will realize it heats up. So that is part of energy is being lost to your surrounding. All right, so I think that's most of it for electrolysis. And previously we talked about the production of chlorine, okay, the chloralkali process from a concentrated sodium hydroxide and sodium chloride solution, right? In another case, like industrially, people can do electrolysis on molten salt. So basically you heat it up to a very high temperature that's over 800 and 900 degrees Celsius, then you get a liquid. So our traditional E-cell, like this standard potential, this was developed for solutions. So in the case of molten salt, this no longer apply. So let's think about an example. If you mix sodium bromide and magnesium chloride, okay, and then you heat it up, melt this mixture, and connect to a power source. You're doing a electrolytic reaction. How can we determine what gets reduced, what gets oxidized? Since I mentioned this no longer valid, right? This still with aqueous solution. Now we're in a pure molten ionic substance. We can either look at the ionization potential. So this basically describes how strongly this atom is holding on to its electron. So if you think about a redox process, it's about giving electron away and getting another electron to change your oxidation state, right? And another thing, we look at its electronegativity. We know fluorine is the most electronegative one, right? So as you go down the periodic table, it becomes less electronegative. That also has to do with atomic size. Ionization potential, we know that it's increased from left to right. Based on this, by looking at the periodic table, we can guess magnesium will be reduced preferentially. And then by comparing the electronegativity, we can figure it out bromine can lose its electron and can be easily oxidized, which will happen at anode. Okay, remember the convention for electrochemistry is anode is oxidation. Then we can simply guess the net reaction of electrolysis of this process. So generally you would liquid magnesium and bromine gas. And these things are in this gas, the bromine is in gas phase, so that has to do with the temperature of your reaction system. So this is the example 21.9 that I'm referring to. I think someone asked me about where does H plus and OH minus concentration for the KW come from. So if you look at the page 978, there's a description. It's telling you that under conventional definition in electrochemistry, everything for standard state is at 1 molar, right? But for water, it will dissociate to a very small extent where you're at the concentration of 10 to the negative 7. So that's why the electropotential is not the standard electropotential. And then generally, for the salts such as sodium sulfate that's commonly used in these processes, like I said before, because water is more prone to this redox process and you're generating gas and increasing entropy, it's a good thing. So they will be reduced and oxidized first to generate hydrogen and oxygen. And then the last part of this is just a simple calculation. When we look at a voltaic cell, when the battery is generating current, what does current really mean? It's usually in amperes, right? And then so that is defined by charge over time. And we know electron has charge, right? Faraday's constant give us a definition of how much charge is carried per mole of electron. So in the electrolytic process, we can actually calculate. Now go to your page 980. If you go through these processes, you can figure out how much energy you would need to produce metal to carry out these redox processes. Okay, so I would suggest you to look at Faraday's law and the stoichiometry of electrolysis and go through that. Then we will, as a group, you guys can work on the sample problem 21.11. So these are just simple manipulation of math. So you can figure it out how much electricity, or in terms of current, how much electrons you need to inject into your system for your chemical process to happen. So now we can take a break.